Does it make any sense? You want to see it again? You always have some questions.
No,
What is your name?
Novica.
Novica. Okay, Novica is the you see the spokesman of the class. So tell us.
Union leader.
Yeah, union leader. Yeah.
It's not very clear.
Sorry?
It's not very clear. I think.
It's not very clear.
Doesn't make a lot of sense. This the graph there.
You don't understand it. So
So.
that's good. I mean, it's good that you say that. It's not good that it's not clear, but it's good that you say that because it would be worse if nobody says that and it is not clear. So what are the three most unclear points according to you? Then we go back to that aspect. Because this stuff, believe me, it's simple if you get it. But the first time I studied, I actually was quite confused. So you should not feel. I mean, it's a bit different from the other topics. For that reason, it's, how do you say, it's a bit of a change of perspective, and it's tricky. I don't think it's mathematically complicated, but it's tricky. That's the way I see it. So what is particularly mathematical?
Your eigenvalues, eigenvectors come to play.
Yes, okay, that's a good point, yes.
That's,
Yeah, so let me repeat it again. So we have a graph, and we don't have data points, but the graph could be built on data points, but this is the way we're going to use this on data. But in order to understand this stuff, you can just think of the graph, okay? And the meaning of the graph is that connected vertices are similar, okay? I think this is clear, right? So we have a graph, and the links in the graph means that you can go from one vertex to the other, which means that they are close to each other. That's it. Okay? Now, the graph is an abstract object. So if it is a planar graph, which means you can put the vertices on the graph and connect the vertices without crossing, it's good. You can look at it. But, you know, you can also move, do a deformation of the graph, right? So what I want to do, I want to replace the graph, right, with, I want to replace the vertex of the graph by points in a k-dimensional space, and here we have discussed a one-dimensional case, so there will be points on the line. In a moment we will do a two-dimensional representation, and then we will do the general case. So I want to replace my graph, each vertex on the graph, with a point in the space, such that when I look at the points in the space, that is a visualization of what the graph is. Right? So if I see that two points are close in the space, and these 2 points would be this for one vertex and this for the other vertex. If they are close to each other, it means that the two vertices are similar. Right? Of course, if the two vertices are connected, the 2 points would be close to each other. But I could also take 2 vertices that are not connected on the graph, which happens to be similar when I look at the visualization of the graph in the space. So that's the idea. So I want to do, I want to visualize my graph. Right? And why do I want to do that? Then we think, for example, of the digit example. Right? So the graph is built from data using a similarity matrix, similarity function, which comes from the Euclidean metric. So I have images of digits, and I compute the distance between 2 digits, and if this distance is small enough, I put an edge. Or if either one of the other is a k-nearest neighbor, is a nearest neighbor, something, I put an edge, right? So the graph is a way to connect similar objects, right? That I cannot visualize it. Perhaps here I should have some figure, but I don't have it. So what will happen, right, is that you build this graph from the digits, and then you do a 2-dimensional embedding. So you replace each digit, each vertex of the graph by 2 numbers, right? So what will happen is that the vertices go to the plane, right? So I will see something like that. You believe me, that's what will happen. I think it's an exercise, perhaps, in some coursework. Otherwise, I think if you want to understand this stuff with your hands, which is always good, that is the exercise which I recommend to do for fun when you have time. I can assure you this is fun, but you need to have time for the theater fun. So you can do it during the Christmas or later, but believe me, this is not a difficult exercise. So you take the data points and you build a graph. And the way you build it, there are different ways to build it, but it should be built so that the edges carry the similarity. Right? So the way I describe here is that you take every point and you connect it to another point if either one of the two is a, say, 3 nearest neighbor of each other. Is it clear, right? And then you have the graph, this habitat object. And then we compute this embedding, which I haven't described in 2 dimensions, we'll describe in a moment. But what will happen is that all these are 1, all these are 2, all these are 3, and so on. So the representation that you obtain by doing this machinery, which I haven't described in detail, right? So, but the end result of the story of replacing each vertex, each data point, by 2 numbers, is that points in the same class will be close to each other. So this is a way to find a nonlinear representation of the data. Right? And the way it is nonlinear is that you first build the graph, and then you look at the eigenvectors of the graph in Gaussian. Right? And as we now began to describe, and then these eigenvectors give you the embedding. But the whole process is nonlinear. Right? Because it's very different from principal analysis. So, right? And this representation minimizes some distortion measure, which is this. Right? So, for example, here we do it in 2 dimensions, right? So this x1 through xn. So n is the number of vertices, my data points, for example. What I called t in the previous slide, but don't need to think of data points. It's the number of vertices, right? I want to replace each vertex by 2 numbers. So x1 and xn are 2-dimensional vectors, right? Okay. So I replace each vertex by 2 numbers, which would be the points here, for example. And I want to find these numbers, right? So that this function is minimized, right? I mean, this is tricky to understand. I completely agree with you. It's a bit tricky to understand. Although I think there is some, it follows some common sense also, this objective, right? So you want xi to be close to xj whenever the 2 points are connected. So what this function uses some local information on the data. It uses some local information on the data, right? Because it looks whether the 2 points are neighbors, so whether they are connected. So we have decided to connect them. But by solving this problem, you get a global representation of the data, because each point, each vertex will be replaced by this 2-dimensional vector. So this is what the method does. I think perhaps the most difficult thing is to accept why you do this. But once you accept that this is the problem that you have to study, the solution follows from that. So that's the first difficulty, understand why you do that. The second difficulty is to understand how you do it. Perhaps the second part is a bit more standard, because it's not so different from what you do with PCA. But why you do this is a change of perspective, I think, perhaps. I don't know. Does this add useful information to the problem? Now, technically speaking, you also have some constraints. So here, so this is the planar embedding, the 2-dimensional embedding. Right? So we require. Oh, notice that I call x1, right? Is the first. So because these vectors are 2-dimensional, right? So I can also look at this as a matrix, x1, xn, right? 2 times n matrix, right? And here, x1 is the first row, and x2 is the second row. I think one difficulty with all this stuff is to be comfortable with linear algebra. That's why if you do some of these things in MATLAB, you see that it's not black magic. Just, that in this case, the matrix is two-dimensional. It has 2 rows. And so here we require that both rows are orthogonal to the constant vector, so they sum to 0. Right? They sum to 0. And we require that they are orthogonal to each other. So our two-dimensional representation, two-dimensional embedding, is right, the set of two-dimensional vectors, such that when I think of this as a matrix, both rows are sum to 0. They are orthogonal to the constant vector, and they are orthogonal to each other. And they have L1 norm equal, L2 norm equal to 1. And then what you can see is not explained here in full detail. But the solution of this problem is obtained by taking the first row equal to U2, so the second eigenvector of the graph Laplacian, and the second row is the third. Right? The first you exclude because of this orthogonality constraint. So this slide is a bit dense. It requires some work to be understood. So this is the objective. And the meaning of the objective is that you try to, by representing the vertices by these vectors, two-dimensional vectors, you try to preserve as much as possible the similarity which is represented by the graph. So that's the idea. And since you formulate the problem this way, with these constraints, the solution is obtained by the eigenvalue composition of the graph Laplacian. And so this is it's a very important. This is a very important tool which is used. But this stuff was introduced not much far back in the past. Maybe it was introduced 10 years ago. I think, yeah, actually, I knew the person who introduced the stuff. Which is, I think, we are actually it's a sad story because they are both dead. Now, it's really a sad story. So one is Partha Niyogi and Misha Belkin that introduced these ideas. And the other group was, I think, Soul and Roweiss. So this is stuff which happened in machine learning. I don't know the history behind it, but the idea is to find representation of data which is nonlinear. Right? Nonlinear. Yes. And the caveat of all this method is that if the graph is given, there is no caveat. I think it makes sense. To me, it makes sense. If you think about it, you will see that it is rational. If you do this from data, as we said before, the caveat that you build the graph starting from some distance, and depending on which Euclidean distance, depending on which distance you use, a different graph is obtained. So this then will give you two very different presentations, two very different embedding, but which one do you use? So this is a tricky point, which can be a source of that this method will not work, will not provide a good representation of the data. And these ideas are also used in the context of supervised learning, like principal component analysis. So I have my data points, I apply PCA or I apply this Laplacian embedding, So this is in 2 dimensions, but then you can extend this by taking the k smallest vectors, right? Laplacian, and you find the k-dimensional representation of this. So this can also be used for supervised learning in the sense that you can use this representation as an input to the classifier. Right? So by representing the points this way, then you can look, for example, for a linear classifier of the data. So this repeats what I was saying. So the representation is nonlinear. So when you do this from data, the way you associate your data points t to this embedding is a nonlinear transformation. And it's nonlinear because you have built this graph. So, okay, now in the remaining 20 minutes, I want to discuss a little bit about clustering. And I think who's taking a supervised learning? So yeah, say most of you are taking a supervised learning. So you've seen for sure k-means, right? K-means and the EM algorithm. So it's a way to represent the cluster, right? So data associations. So associate the points to few prototypes, few clusters. That's what k-means does, and it does that by minimizing objective function, also in that case, which tries to assign each point to one of the means, and each point should be close to at least one of the means. Here we see a very different method, which is called spectral clustering. Two given data, find a cluster of the data. Okay, so find the partition of the data into different groups. We discussed only the case of 2 groups, but then there is a way to extend that to more groups. So there are only 2 clusters. So this is the idea that perhaps we have seen also mentioned by Mark Upstill on finding cuts in graphs. So I have my graph, which can be built from data, or it can be stay there because somebody gives me a graph. And I want to remove some of the edges in the graph so that the graph is connected. And by the way, I forgot to say this, but in all my discussions so far, I assume the graph is connected. So I have a graph which is connected, and the graph will be connected if when I build it from data, I use a large enough number of nearest neighbors to be connected. So it's not strange to assume it's connected. Then I want to remove some of the edges in the graph so that the graph is not connected anymore. Right? And in particular, I want to remove the minimum number of edges so that the graph separates into components. And then the first component will be the first cluster, and the second cluster. So this is what spectral clustering is in simple words. The question is, how do I decide whether I remove one edge or not? And this is decided so that some objective function again is minimized. So this is what is the motivation for spectral clustering. So I need to define the cut, right, of J. So J is a set of is a subset of vertices, right? And what is the cut of J? So I have my graph which is connected, and then I want to take the set of vertices in J as the first connecting component, and the complementary of j as the second component. Okay? So V is 1 to n, and then j is a subset of V. Right? So for example, I could have this graph, say, right? And if I take as j this set of vertices, so it would be 1, 2, 3, and 4, and it's 5, 6, 7, 8. The cut in this case is 1, right? Because if I just remove this edge, I obtain these two components. Okay? But the cut formally is the sum over I in j and j in the complementary of capital J. So JC is the complement of the set of Aij. Right? So it's a sum of edges which connect one vertex in J from one vertex in the complement of J. Okay, capital J. So this is the cut of the set of vertices, capital J, induced by the graph, induced by the adjacent symmetries. And now I define my objective function, which I want to minimize in order to find the two connected components of the graph, to the two sub, want to find a subset of the graph such that this subset requires the smallest possible number of edges it is connected from the graph. And I define it this way. It is the cut divided by this quantity. So 1 over the number of elements of the set J plus 1 over the number of elements of the complement. Right? So this will be, this is n minus J. Right? So the sum must be equal to n. And I said JC is J times the complement. The reason for which I define it this way, that you see this term avoids the possibility that either J or the complement are very small. They contain only a few points. Right? So if this favors some balance cuts. So what does it mean? That if, for example, I have this graph, clearly, in this case, if I cut here, right, I remove this vertex, this edge, then I find one component which consists only of this point, another component which consists of all the others, right? But this term will be quite large because it's 1 over 1 plus something small, right? Whereas if the cardinality of J is the same as the cardinality of the complement, this number will be much smaller. So this number tries to favor balance cuts. So in the typical situation, you have like a few thousand nodes in the graph, right? You want to disconnect the graph into components, but you don't want either one of the two to be too small in number. Right? And this happens. So if you build the graph, say from the digit images, right, and you don't put this there, we just disconnect one digit from the graph. So our goal is to find the clustering of the graph into partitioning in two groups, right? By minimizing this quantity. Right? We want to minimize this over J. So it's a combinatorial problem. And then what we will see in time that the problem can also be approximated using the eigenvectors of the graph Laplacian. This is just I think this is the beginning of spectral clustering. Then this is extended to more components, but I don't describe that. If you are interested, I can point you out to some research. There's a review paper which describes this. But I think here you see a good part of the story. The last 3 slides are a bit more technical. So what you see is that a bit more technical. So I define a function f of j. So f of j is a vector, n-dimensional vectors. N is the number of vertices. So fji is equal to one number, gamma, if I is in the first component, and minus 1 over gamma if I is in the complementary component. Okay. And I choose this gamma this way. Is the root of the cardinality of the complement, which is n minus cardinality of j over j. Now, I let you verify as an exercise that since I have chosen this vector this way, so f of j is a vector, defined as here, right? Now I drop the j here, it's sloppy, right? So I just call this vector f. Now if I sum the component of the vector f, the sum is equal to 0. This follows as some algebra using the fact that f is defined this way and gamma is defined this way. It just simplifies. Also, the norm of the vector f is equal to the number of vertices. Right? And now, what you can also verify, since we are a bit short of time, I leave it as an exercise, but it is written here, is that if you take the vector f, defined this way, and you compute the quadratic form associated to the graph Laplacian, so it's f transpose lf, this is exactly equal modulo the constant n to the cut, to the normalized cut, to rho of j, what we defined the previous slide as the cut of j, the number of vertices, of edges which I need to disconnect, remove from the graph to disconnect the set j, the set of vertices j from the graph. Right. And then it was times 1 over j plus 1 over jc. So the quadratic form of the graph Laplacian is exactly equal to the balance cut, so rho of j is the balance cut, times n. Times n is very important. Okay. So the graph Laplacian also measures in some way, when evaluated on the special vector f, how difficult it is to disconnect the subgraph. Right? So the idea then is that if we minimize this over f, subject to some constraint, we solve the minimum cut problem. Okay. So this observation suggests the following problem. So since for this choice of f, this is equal to the balance cut times n, then what I can do, I can try to minimize this subject to the constraint. So this says that the sum of fi is equal to 0. This says that the same there. And this is the, how do you say, is the nasty constraint. It's a combinatorial constraint which is difficult to enforce when we solve the problem. This says that f has the form that I decided to have, right? So this says that f is associated to a subset of vertices, and the component of f on these vertices is equal to gamma, and on the others is minus 1 over gamma, where gamma is equal to. So this is a combinatorial constraint which is difficult to enforce in the minimization, right? So the problem is hard. However, we can do a relaxation, which means drop some constraints. So if we drop the combinatorial constraint, we have a problem which is convex, which is easy. We will see in the next lecture what convex means. But in this case, it's an eigenvalue problem, right? Because we have to minimize these. So we have what pretty much we saw before, right? Because before we call this x, this was the only difference. The F transpose LF. So F is in Rn, sums to 1, the norm is equal to n. So what is the solution of this? Is the second eigenvector of the graph Laplacian, as we saw before, right? But now here the interpretation is very different, right? Because we solve this problem. The solution is F, and solution is F equal to call it maybe U2, second eigenvector. Then we need to remember, then what you do, you look at the sign of the components of this vector, or something like that. And if they are positive, it means that that vertex is in J. If they are negative, it's in the complement. Right? So that's the way that you obtain an approximation of the spectral clustering problem. Right? So spectral clustering is the previous of the min cut problem. So min cut problem is the balance, minimum balance cut problem is the hard problem. This is the spectral. The spectral clustering problem, which is the relaxation of that. And it is solved by the eigenvalue decomposition. And you obtain your approximation for the min cut problem by taking the second eigenvector of the Laplacian and taking the sign as a way to decide the set J, the set capital J. So from this solution, you can extract the set J, which gives you the best partitioning of the graph into components. And then you can repeat this. So, for example, you can take the graph, you split it into two parts, and then this part, you split the argument, you split another two. Same here, right? Or, and these are all heuristics. I mean, this is a research topic that is not well understood. So it's not well understood how well this works in practice, because these are approximation of difficult problems, so sometimes they're not good approximation. But if you want to do a clustering of the graph into more than two components, one way to do it is what I said, but the other way is to take more eigenvectors here. So instead of taking 1 and 2, you can take, say, 2. Take U2 and U3, right? And then, this is completely an heuristic, which I don't understand at all myself. But people use it because the rule of thumb that to some extent it works. So if you want to find 3 components, you take the 2 smallest eigenvector, excluding the first, which is the constant vector, and then you do 3 means clustering of the planar embedding of the graph. Right? So these 2 vectors give you a planar embedding. You take the first one, the second one, right? These are n-dimensional. So each vertex of the graph has 2 dimensions, 2-dimensional representation, right? So let's say that you do this for the digit 1, 2, and 3, right? Then you have this matrix, right, which is 2 times n, and then you map the digits, which are the vertices of the graph, in the space, and you find digit 1. This is not as beautiful as this, but it's about like that. Right? Digit 3, right? And then you apply k-means, right? And k-means will give you an easy answer in this case because the different digits are well separated. But I made it easy. There will be perhaps a little bit of noise in between, right? So that's the way to use spectral clustering for more than 2 clusters. Two clusters is what I described for more than two. One way is this, but it's an heuristic. If you read some recent papers in the literature, that's what they say, it's an heuristic. So this is a topic where there is still a lot of work to do. And this stuff is also used in computer vision, so perhaps if you are taking some computer vision courses, this is the last thing I say. It's also used in computer vision. You take an image, right? There's a landscape, something like that. And then there are many pixels, so 500 times 500. Right? And then your graph consists of all the pixels in the image. Right? And then you decide that two pixels are connected, so you put an edge depending on the difference of the gray value, or something like that. So this way you have your graph is like, and here they do it weighted, so that you weight. So there are edges between every neighboring pixels. So right, so it's like that. One pixel, one. It is how the graph looks like when it's centered into this pixel, then it continues, right? And the weight depends on how similar the gray values are, or something along those lines, right? Very much hand waving here. But then you look for a partitioning of the graph into different regions, right? And this is the way to do segmentation of the image, right? So the region should be of similar color, similar textures. This is an algorithm which is using computer vision, and it is one of the first contexts in which this idea of mean cut was applied. Okay. Just for fun. But if you take the computer vision course, perhaps it is mentioned. So I hope this lecture was useful. In the exercise, there is only one exercise for the exam. If it was useless, just try to do the exercise. If it was useful, I'm happy, interesting, I'm happy to tell you more. So in particular, as I said, there are